one is the easy part. What is really tricky is the uniqueness result. So let me give you some ideas for the uniqueness of this weak solution. So I start from two weak solutions, U1, U2. They have the same initial data. U0. As before, I consider the difference between the two. I write down formally, because everything should be expressed in a weak sense, but I give just general ideas here. Formally, you have this kind of linearized Euler equation on your difference V. Of course, the fields here are not so regular, okay? So I write it in the classical form, but you have to be careful. And then, okay, we did that for smooth solution. I can multiply by V, integrate. And you get that d over dt of the epsilon squared is less than the absolute value of v dot gradient of u2 dot v. This is the calculation we have made. This term disappears because there is this nice cancellation property, and you are left with this one. So you remember that last time, for smooth solutions, we had a similar bound. And we said that it was less than the gradient of u2 in L infinity times the square of the L2 norm of V. That's what we did last time. But here we cannot do that anymore. So, for weak solutions, the problem is that, okay, for smooth we have that and we conclude by going up. But for weak solutions, you cannot do that. Because omega 2, which is the vorticity, is in L infinity. But the gradient of u2 is not. Okay. That's what we had discussed earlier, right? Go from omega to the gradient of u. In L infinity, it's not good. So again, we cannot use the classical Gromov inequality. Okay? We have to be smarter than that. And we know that we have LP bounds. So we will try to use these LP bounds. But I have to know about the way the constant that I denoted CPs at some point, I have to know how it depends on P. Okay, so we had seen that the gradient of U2 is less than some constant in LP, is less than some constant depending on P times omega in LP. But actually, we can state something a little better. Well, we state it like in the book by Maida and Bertozzi. So for all compactly supported field omega, the associated velocity field satisfies the norm of gradient of U in LP is less than some constant involving the L infinity norm of omega times P. Actually, you can say CP is P. CP is bounded, but I don't know why to formulate it like this. So you see this constant here. You can keep in mind that this constant here, we have a detailed information on how it depends on P. It's linear in P. Linear in P. So this will be useful because we come back here and now we use this information. So d over dt of the L2 norm of where the V is less than what? So you see we have, it's less than the norm of gradient of U2 is the norm of V squared. And we use Hölder inequality. So we say this is less than gradient of U2 in LP times the norm of V in L to P prime, and there is a 1 over 2. Next, we use the proposition. So the gradient of U2 in LP is bounded by P times something which is finite, because we work with bounded vorticities. Okay, so it's controlled by the L infinity norm of the initial velocity of vorticity. Okay, so this is a constant. So I denoted C. But what matters here is the P. Okay, so you have C, P, and then you have this guy. So you have the L 2P prime norm squared of V. If I could take P prime equal 1, then P equal infinity, I would be done by one value argument. But of course P prime is usually greater than 1. Okay? So I would like to have some differential inequality on this. So I will try to make appear some L2 bound here. So I have to do the following. I have to say that this L2p prime bound, careful with the exponent, you can check that it's less than the L infinity bound on V. So that's 2p prime minus 2 over p prime times the L2 bound on V 2 over p prime. Okay, so in this, so you see in this L2p prime bound, I have V to the power 2p prime, and I want some 2. So I put everything in the remaining in L infinity. But the problem was controlling gradient of V. For V itself, no problem. It's controlled by the L infinity norm of the vorticity. So this is bounded by some constant. Okay. So what we get is the constant times P times the L2 norm of V to the power 2 over p prime. So if we use notation E of t is L2 norm of V of t squared, what do we have for an inequality? We have that E prime of t is less than constant times p times E of t to the power 1 over p prime.